Welcome back, everyone. We are continuing our study of assembly language programming in the context of microcontrollers. In this video, however, we will be changing focus to a different class of instructions, the program flow instructions. Previously, we had been studying both data movement and data manipulation instructions, so we're going to change focus here. This video is only an overview of what these program flow instructions are and how they work. In subsequent videos, that's when we're going to go over the details with some examples. So this figure should look familiar. Your program is assembled into opcodes and operands that are put into program memory. Program memory starts at address 4400 for the MSP 430 FR6989, 4400. And when you execute a program, the program counter points to the address of the next program instruction to be executed. So when you begin your program, the PC program counter will be initialized to 4400 in hex. The fetch operation consists of putting the address held by the PC onto the address bus, retrieving the instruction from program memory, and bringing it back to the control unit so it can be decoded and determine what to do next. So we're starting at 4400 as shown in this figure. That's where our program lives. Under normal operation, that is operation with only movement instructions and data manipulation instructions, instructions are assembled and packed within program memory one after another. The program counter starts at 4400 and just, marches down in the figure, that is, actually increasing its address. So the program counter is just sitting there marching away into program memory. The MSP 430 instructions are either 16-bit words, which are 2 addresses, 32-bit words, which are 4 addresses, or 48-bit words, which are 6 addresses, it turns out. And the number of addresses is known to the assembler by the opcode. So the program counter then just keeps going accordingly. It knows where to march along to. Your program memory is finite, of course, and you can observe right away from that the program counter will eventually march out to where you don't even have instructions, or worse yet, wrap around to other memory like for peripherals or data memory. In this case, the program counter doesn't know. It just keeps pulling the addresses. And so you're going to get like a program execution that might halt for an illegal opcode. So we're going to want to alter the program counter beyond its normal, that is, sequential operation. If we just had an instruction that could redirect the program counter to a memory address that was previously encountered, let's say, then we would have a way to loop through the program much like a while or a for loop would. And we would have a way to run a program that runs continuously. And let's consider a different scenario. Let's say we're marching right along, the program counter through program memory, and we perform some sort of calculation. And then, as a result, we want to skip some lines within the program. These skipped lines, I don't want to execute. So we would increase the address of the program counter to skip those lines. And that is what gives us the possibility of if-else or case statements. So like, for example, if you code an if-else statement, you would provide statements that are executed if the if statement is true, and you will provide statements that are executed if the if statement is false. The way it's handled in the machine is that the opcodes and operands of both groups of statements are stored in program memory. Which of those blocks you execute depends on some status, emphasis on the status, just before it's calculated. Then you just skip over the block, jump over the block you don't want to execute by increasing the address in the program counter. A case statement is similar. If you had, say, 8 cases then opcodes for all 8 cases are stored in memory, but maybe 7 of them are skipped or jumped over by altering the program counter. So we need instructions to explicitly alter the program counter. In assembly, that's the notion of what we call jumps and branches. These are new terms to us. Of course, they're related, though, to loops and conditional statements. There are instructions that alter the program counter so it deviates from the address of the next instruction to be executed as it marches along. These are all considered to be part of program flow, that is, implementing code that executes based on inputs, a dynamic execution instead of one that is static and prescribed in the binaries. Jump, branch instructions may be unconditional or conditional. An unconditional instruction alters the program counter no matter what. So you can think of like a while true loop. No matter what, that loop is going to happen. And depending on your education, you may be thinking that a while true loop is not a good thing. Okay, but let's kind of consider that we do want actually programs to run continuously forever. For example, your operating system runs forever, right, as long as it has power. A pacemaker is an example of an embedded system that we've talked about before. You want your pacemaker that you insert in somebody to run continuously. You don't want it just to run once and then be done. Certainly not. And a control system in your car, you want to run continuously as long as that control system has power. It might not be doing anything, but it's running continuously. A conditional instruction only alters the program counter when certain conditions exist on the VN, I've got a typo there, VNZC status flags in the status register. But that's pretty cool. We said status, right? So that's the VNZC status flag. So remember that the ALU is manipulating the data arithmetically and logically, and it's keeping track of these VNZC bits. We can have, it turns out, program flow depending on those VNZC bits. So that is really a cool thing. And then I want to point out that address labels are essential to program flow instructions. As the complexity of the program grows, there is little chance, no chance, that you, the programmer, will want to remember the absolute addresses. So you're going to want to make good use of address labels, certainly. In this figure, I've got most, or actually all, of the program flow instructions, and then some other miscellaneous instructions thrown in for good measure. So you can read some of these on your own. I'll point out a few of them. JMP is jump, and you'll see the description, jump always. You'll see JEQ is jump if equal, JZ is jump if 0, and then you'll see below that JNE, jump if not equal, JNZ, jump if not Z, JC is jump based on if C is asserted, the C bit, jump if not C, if C is not asserted, and you'll see also the branch instruction below. So again, I want to point out that some of these depend on the Z flag. They're Z flag based jumps, right? So that's really cool there. And some of them are C flag based jumps. Nice. Now notice that there are a couple of pairs of mnemonics. For example, JEQ, jump when equal, and JZ, jump when 0. These things do the exact same thing. They jump when the Z flag is 1. So, of course, you might be wondering, why on earth would we have two mnemonics that do the exact same thing? Well, the interpretation is different, and the two different names can help the programmer remember the mnemonic or remind the programmer what the line is doing or why it is there. Do you remember the compare mnemonic, CMP? To compare the source and destination, the assembler subtracts the two and looks at the Z flag. And if Z is 1, then we know that they're equal. So thus, jump if equal looks at the Z flag to make the distinction of equal. Jump if 0, of course, looks at the Z flag to see if it's 0. See if the Z flag is 1, that is. So you can understand how these two things are equivalent, but with a different interpretation. The pair jump below it, jump if not equal, and jump if not 0, right underneath, they're similar. There are two unconditional program flow instructions, which we said was jump, JMP, and branch, BR. As they're both unconditional, we're going to need to understand the difference. Branch is the simpler of the two. It moves the value of the source operand into the program counter. So it does exactly what you think it would do. You give it an address, and then it moves that address into the program counter, any address that is within the program memory. You would probably want to specify the operand with immediate mode addressing to specify the address label, right? We're not going to keep track of these actual addresses. We're going to label addresses. But the problem with branch is that it turns out it requires a whopping 3 words of program memory. If you remember, I said that instructions are either 1, 2, or 3. So this is actually a slow, relatively, operation, slow relative to the jump instruction, JMP. So jump is added just for speed. It uses 1 word of program memory. And you might say, well, what's the catch? Like, why? Like, how can it do that, right? So the catch is this. Instead of specifying an address, it applies an offset to the current program counter. This is what improves its speed. And the offset cannot be just anything. It's limited to integers between -511 and +512, which means the jump location needs to be close in memory to the program counter. Otherwise, the assembler gives an error, jump out of range. For example, this is perfect for if-else and case, where in your code, your if condition and your else condition are very close in the program. But if we have to jump, say for a loop, from like at the bottom of a huge program back to the top of that huge program, then we might actually find that the jump is out of range. And in that case, you have to use the branch, the slower instruction. Now, I do want to point out that you, the programmer, don't specify the offset in the jump instruction. Rather, you usually use symbolic mode addressing, and the assembler calculates the offset. All right, well, remember that this is just an overview of program flow instructions. Next time, we're going to look deeper into these instructions with some examples. As always, thank you, and I will see you next time.